I've written the results of KVL and KCL to the differential segment of transmission line here again. We find from KVL that the derivative of the phasor voltage at the input end of the transmission line is just equal to minus times R prime plus j omega L times the phasor current at the input end of the transmission line. And from KCL, we find that the derivative of the current at the input end of the transmission line is equal to minus J prime plus J omega C prime times the phasor voltage at the input end of the transmission line. So these are just relating the rate of change of voltage to current and transmission line parameters, and the rate of change of current to voltage in the transmission line parameters. What we're going to do next is we're going to take the derivative of this entire equation right here. So we're going to take d dz of this equation, and it looks scary, but it's not too hard. This just becomes the second derivative of voltage, with respect to time. This is a constant, right? There is no distance dependency on this. There's no z dependency on this, so we just pull this out front. And then the derivative of the phasor current as a function of voltage is just d I of z dz. So we've taken the derivative of this equation, and this is our result here. We notice that di of z dz we've already solved for in terms of voltage right here. So what we're going to do next is substitute the result from Kirchhoff's current law analysis into this equation. And so that gives us the second derivative of voltage at the input end of the transmission line is equal to minus R prime plus j omega L prime, so the transmission line parameters, times minus G prime plus j omega C prime times the voltage at the input end of the transmission line. So we can see what's going to happen here is that these signs are going to cancel, and I'm going to use a different notation here. V bar double prime of z, the second derivative of the voltage, is just equal to R prime plus j omega L prime times G prime plus j omega C prime times V of z. So we can rewrite this as V double prime of z minus 0 times V prime of z minus R prime plus j omega L prime times G prime plus j omega C prime times V of z is equal to 0. And a lot of times this is just made more simple by writing V double prime of z minus gamma squared times V of z is equal to 0. And here we're saying that gamma squared is equal to R prime plus j omega L prime times G prime plus j omega C prime. We just did that substitution, and therefore gamma is just equal to the square root of the right-hand side of this, R prime plus j omega L prime times G prime plus j omega C prime. Just the square root of that whole term. So we've done a little substitution, we've just changed notation a little bit, and we're left with this equation right here. This is called a second order differential equation. You take the second derivative of it, and there is a general solution to this. However, you've not learned the mathematical techniques in class yet to solve this, and in fact you wouldn't until you took a calculus like differential equations or something like that. So I'm just going to give you the general solution to this. And the general solution is that v bar of z is going to be equal to something called v bar plus e to the minus gamma times z plus v bar minus e to the plus gamma z. So this is the result of the analysis of the second order differential equation right there. And this is very important. This is a equation that we will be using throughout the rest of the remainder of the course.